All right. Hello, my name is Justin. Today I'm going to be doing a little recording that introduces the R programming language. This is for the data mining class at UNT for the summer 2024 semester. R is a very interesting programming language, and it's also something that a lot of people may be unfamiliar with. So today is just a brief video that introduces all the sort of important parts of the language. So I have a few different views of this video that I'm going to be going through. I'm just introducing the very basic parts of the language. The thing that you'll probably end up using for programming in R is this program called RStudio. Right now, I'm not going to be using that. I'm just going to be using the regular command line prompt. You'll probably use something different in your own computer. For my computer, I use a special operating system, and I just use the R command, which is just it's called a REPL, a read eval print loop. And so you just type in stuff here directly, and it evaluates each line of code, and then it prints it out, basically. So you'll probably end up doing something a little bit different. I'll probably make a video about RStudio in a little bit, but for now, we can just go through this. So all the code that I'm going to be showing off today is on the left side. I'll type it in on the right side so you can interactively see the output. But I'll attach these three output files as well for you to utilize if you would like to do that instead. Also, everything I'm going over, I learned myself based on the W3, I think the website is called W3 Learn. If you just Google learn R programming language, it's one of the first things that come up. So let's get started then. So to begin, if you're familiar with Python, for instance, R is very, very similar to that. It shares a lot of similarities to Python. Specifically, I think it's called the Pandas data library. A lot of the things you're going to see inside of R, it bears a lot of similarities to that. Specifically things like data frames, lists, vectors, well maybe not vectors, but tuples are very similar to vectors. Just the general way that R treats everything as first class, very similar to Python. So let's get started. If you were to run this R program, you can use something different. In fact, I like to do, on the left side, we can see that this is a program on my computer. You can just go ahead and do something like, let me go to here it is. If I were to, there's this file here, helloworld.r. It's an R file. It's the same one you see on the left here. But the point is, if you run this command R script, if you've used the same compiler that I'm using, I think it's just when you download a package called R in Linux, you can just run R files here, and it evaluates every sort of line of code, basically. So let's get started with the interactive version, which is instead of running the entire program, it just runs each line as its own sort of discrete unit. So starting off, we have everything in every line, at least in this version of R, this compiler, this interpreter, I should say, this REPL. Every line of code is evaluated and it returns something. If that line of code does not return anything, then it is not displayed. So we can see here, hello world, this string, which is encompassed by quotes, that value gets returned to the REPL. It gets returned to the interpreter, to the compiler. And whatever you type in, if that returns any kind of value, then it will get displayed. So I can even type out some kind of math statement here, like 3 plus 3, and this returns 6 in this case, because this line is evaluated and it returns that value. We can type in comments here. So here is an example of a comment. Just like in Python, you can add a pound sign to the front. I don't believe there are multi-line comments, so you just sort of add a bunch of like you can see on this left side, you just add a bunch of pound signs, and that represents a multi-line comment, basically. So assignment is done by using the sort of, we can call this the arrow operator. It's the first big difference between other languages. Most of them use an equal sign. Some languages like OCaml, I think they use a sort of symbol like this. The purpose of it is just to show direction. It's different from like a math perspective, which R is a little bit more similar to like a mathy programming language. It's a very nuanced description, so you don't really have to worry about that. I think you can do the equal sign too, but the differences, there's a few differences that we don't really need to get into right now. So just stick with the arrow. So for instance, I can say X arrow 5, and now X is an alias for the value of 5. So wherever we use X, so for instance 3 plus X, we can see X gets replaced with that value. Just like any sort of standard imperative programming language. So we can also do it the other way as well. If we were to say 5, or let's say 7 goes to X. So previously we could have read this as X is set to the value of 5, or 5 goes to X, and now we're going the other way around. 7 goes to X. And now if I were to do 3 plus X, this is 10 now. We can, using this sort of system, we can see that this is our first thing I said earlier. X goes to 5, that does not get evaluated as a value in the REPL. So that's why it's not, it doesn't return anything. So that's why it's not displayed in this sort of interpreter. Using this sort of structure though, we can chain together sort of assignments. So if I were to say A goes to B, which goes to C, which goes to 9, and I were to do A plus B plus C, that C gets set to 9, then B gets set to the value of C, which is 9, then A gets set to the value of B, which is 9. So now we add them all together, it gets 27. All right, so the next sort of big thing we can see here is that we have functions that we can invoke just like any other standard programming language. The variables that we have in our language here, like X, there are a few sort of things I should point out. A variable, I think it has to begin with a letter, then you can have anything following it. So this is a valid variable name. You can have A, and then you can have a bunch of numbers following it. That's also a valid variable name. If you have, it has to start with a letter. If you have a number that starts with it, like 8A, this is not a valid variable name. But the big thing I should point out is that in R, it is completely okay to have a variable name start with a period. So we can say ABC, this is fine. So I can say 4 plus dot ABC. You'll see this come up in some libraries, so it's good to just memorize that this is a thing that is able to happen. I'm not sure if you can have it in the middle of a variable. We can just see that right now. C dot XYZ goes to 5. And if I were to say 1 plus C dot XYZ, yep, so I guess that is allowed. That's pretty interesting. So this is a cool thing about the language. Okay, so let's go ahead and continue then. So with our functions, our procedures, I should say, we can invoke any kind of procedure with a specific name. So if we were to have some kind of procedure, for instance, named paste, which we're going to see what this does in just a second, just adding parentheses afterwards and it will evaluate that. In this case, this didn't really do anything helpful, but if we had a special procedure, we can evaluate it just by doing parentheses afterwards. Also important to note, this language does not have semicolons that end each statement, unlike something like Java, which does, Java, C++, C. So, but let's talk about what the paste function does. Paste, what it does is it combines two sort of values into a string. So let's say I have the string hello. I think we can do this with a regular plus for just regular strings. Hello world. Non-numeric, right, so this does not work for strings. We already saw what happens if we do that with numbers, it'll add them. But if we wanted to add two strings together, we cannot use the plus sign. What we have to do is we use this function called paste. Paste takes in a variable number of arguments, so any kind of variables you pass in, you can have paste one thing to itself, or two things, or 100 things. So let's say hello is the first argument, world is the second. So, and this returns a new string. So it's not related to either of these two parameters. So it's a brand new string, brand new section of memory that is the combination of these two other strings. You may notice that there's a space that is inserted here. Just to see what this looks like, if we were to have this optional parameter called sep for separator, then we can set, let's say, a $sign. Let's say something crazy, like $3. Now, it's no longer a space, which is the separator for adding these two strings together. We do hello, then the separator, then world. And you don't have to worry about that right now, but the main idea here is that similar to Python, we have named arguments which you can set the value of, which is just an interesting thing. We're going to see more creative uses of that later on. Okay, so we can see, here's a first sort of nice example with a paste function. Let's say I have a string like this. I have first name, which is, let's say, Justin. Last name, which is my actual last name, Garrigus. And now, if we wanted to add these two strings together into a full name, then we can say full name is equal to whatever the value on the right is evaluated to. In this case, I want to paste first name and last name together into a new sort of string. And of course, I can just type out full name here. Full name is a value. It's going to get evaluated by the REPL, and that's going to get displayed. And we can see these two strings are put together with the separator, which in this case, the default separator is a space. Let's say I want to have something different. Let's say I also have middle name, which is Matthew. This is my also real middle name. And now full name, I'm going to overwrite this value by saying full name is paste first name with the middle name and with the last name. And I'll type out full name again, which is Justin Matthew Garrigus. Great. Let's say I want to do something crazier here. I'll say full name is paste first name. I think I can do up arrow here. Yeah, so on this specific REPL, I just do the up arrow and it'll do the last command entered. I'll say the separator is a comma. For instance, if I was going to do a CSV file, and now we can see it's Justin, Matthew, and Garrigus all like that. Great. So let's continue. There's different types of values in this language. You can notice here that we do not have to specify the type of a variable before we utilize it, which is interesting. It's different from C, which if I wanted to have an integer, for instance, in C, I would have to say something like int my variable is equal to 5, something like that. And that, of course, does not work in R. An equivalent statement would just be saying my variable goes to 5. Or I guess 5 goes to my variable. So there is no explicit type that we associate with this. It's all implicit. I think the name of this type of language is weakly typed as opposed to strongly typed, which is explicit. I may be wrong about that. But, of course, all of these variables have to have some kind of type stored inside of the language itself. So that something has to associate these variables with a type. So where do we get that? How is that stored? We can use the class function, just like paste, how paste is the name of a specific function. Class, if we pass in a variable, for instance, my variable, which I just made up here, it's going to tell us what the class, what the type of it is. I think we can also say type of my variable. So yeah, you can see here, there's a little bit of nuance for what these two do. I think the difference is class is more general. Maybe class is like a superclass. It's a very nuanced idea. We don't have to worry about that. But we can look at this class. My variable here I said is 5, and you can see that it's evaluated to a double as the type there. A double is more for like decimal values. If we want to do a actual integer value, we can say my variable is 5L. L here meaning long. It's a C thing, but now we can see the type of my variable is an integer. The class should still be, I guess the class here is an integer now. Okay, that's interesting. Maybe numeric is for floats. I'm still learning about this language too as well. There's a lot of nuances that I'm not entirely certain on, so we'll learn this together. Okay, so these are the types. If we want to get the class of something, the type of something, that'll be helpful there. We'll see later on another situation this is helpful in, specifically when it comes to functions. There's a lot of really cool sort of things we can do with functions that something like checking the class of a variable would be very helpful in. Okay, so let's move on. The class of a string, like full name up here, is character. So this is actually very interesting because you may think that if we were to take Java, for instance, Java has a char data type and then it has a string data type. So there are two separate data types for a collection of characters and then a single character. So that is different from this language where we only have a string represented as the type of a character. And we'll see a really, really cool idea about this language in just the next part of this video. But for now, just take that as at face value. It's a very cool sort of idea, so we'll see what that is. So let's continue to this next part. If we have a string here, we can learn a little bit more about strings. Strings have this function nchar, which we will see here, full name. This just returns the number of characters inside of a string. So in this case, there's only 23 characters. I'm sure if you type this out, if you counted this out, it would be 23. I probably shouldn't type that out. Okay, yeah, but you can see there. I think you can also do length. And this is actually 1. Okay, so we're going to see length more later on, but for now, ignore that. Nchar, this counts how many characters there are in the string. Just a few more minor things. If we wanted to cast different variables together, as integer can cast let's say a floating point value like 3.14 into an integer. This does, we can see it just gets the floor of the value. If we were to say as integer, and then we were to say the class of that, now the type of it is integer. So the way we read this, if you're not familiar, is we evaluate this inner part right here as integer. This gets evaluated into, for instance, 3, and then we get the class of that. So it like builds from the ground up. All right, if we wanted to do multi-line strings, I'm not sure how this will look here, but we can see. A multi-line string is as easy to do as just not closing the string. At least on the left side, we can see it works over there, but I'll say, hello is there, world, my name is Justin. And now we have these escape characters here, these \n's. If we were to, or in this case, I didn't store into a variable. Let's just say a is equal to, or let's say it's more descriptive. Multi-line is equal to hello, world, Justin. And now if I were to print the multi-line just by saying that, it will get displayed like that. So let's now draw a distinction between the methods of printing. In R, for all the things that we're going to be working with right now, for at least this video, we're working inside this REPL, which is, like I said earlier, every line of code you press enter on, it's going to be evaluated by the interpreter, basically. That is then going to be executed, and a value will be returned from that and displayed to the screen. Sometimes the definition of a single line of code will get a little strange. And I don't want to dwell on this part too much, but print a variable. If you're familiar with Python, then this will make sense. It's just printing something to the screen. This is equivalent, basically. So I can either print out the variable itself by saying, in this case, multi-line, or I can just explicitly say print. Sometimes print is going to be required. We'll see those situations in a moment. If I wanted to have printing to the screen that includes these new line characters that are actually displayed, those new lines, I can say the cat command. Cat, short for concatenate. And you can see hello world Justin. It does not include the trailing new line. If I were to say, for instance, multi-line is equal to paste multi-line, a \n, and the separator is nothing. Now, if I were to print multi-line, this now includes that \n. So I've just appended this \n to the string. And now I can do cat for concatenate, multi-line. Now that gets displayed with a \n, so now it doesn't have that weird sort of effect that is now cut off because I press enter, but now it's all displayed correctly, or as we would expect. Okay, so let's continue. Another small thing that we can just check out right now. Let's say that I wanted to see if a string existed inside of another string. What we can do is to use this grep_l command. Grep, I forget what grep stands for. It's a popular Linux command, grep. If you've done anything with Linux before, or I think Mac as well, you may have looked at the grep command. It's just a way of searching a lot of files for a specific pattern. L in this case stands for logical. So this is a helpful command for us to see if something exists in something else, and then tell us true or false if it does. So for instance, if I have a grep_l of, let's say, Justin, the pattern is going to be Justin, and the search corpus, the body of text we want to find this pattern inside. We can even say Justin is the needle, then the second string is the haystack. Let's say the string is my name is Justin. This, in this case, evaluates to true. So Justin was found in the second string. My name is Justin. We can see it's right there. If I were to change this to capital J, now this string here, Justin, is no longer found in the second string because the character here, which is lowercase in this first time, uppercase the second time, they're now different. I think we can do patterns inside of here, but I'm not confident on that. So there's definitely is a way to do patterns that are not just constant strings, but this is a helpful way to just see if a string exists in a second string. Okay, now we can move on to something like conditionals. So this is where the language gets more interesting and more sort of standard for what we would expect. If we wanted to build entire programs that we evaluate and not just do a line-by-line basis, then something like a conditional and if statement would be very helpful. We can do a conditional very simple, just by saying if parentheses, and then we have some kind of condition to evaluate something that is either true or false inside of here. So let's say if 5 is greater than 3, in this case it is, I'm going to print hello and end that. In this case, 5 is greater than 3, so this is just evaluated to true, which prints hello. All good. All right. Let's say we have something more complicated as a condition. So I'll say that let's do something. My name is, or let's just say Justin. Name is equal to Justin. And then we will say if in char, am I doing that correctly? I have to refer back to my little sheet here. In char, yes, it is correct. Name is greater than, let's say, 5 characters. Then I'm going to print your name is longer than 5 characters. In this case, it is. So I can build even longer conditionals. Let's say if in-car name is greater than 5 and in-car name is less than 10. In that situation, we're going to print your name is normal length. I'm sure most people have a name, at least in America, most people have a name between 5 and 10 characters. So in this case, it is true. If I were to rename name to something like Samantha, 1, 2, 3, 4, 5, 6, 7, 8, Samantha, nah. So that's a very long name, at least in America. So we'll say in-car name is greater than 5 and in-car name is less than 10. We're going to print your name is normal length. In this case, nothing is displayed because this first condition is true, but the second condition is false. So this operator AND combines two conditions into one and evaluates that both of them are true. And if both of them are true, then these two conditions are combined to a single condition, which is evaluated. I think we can also do, in this case, we can say and, which is more familiar for Java programmers, C, C++, those types of languages. We can say that, and we can see something, nothing is still displayed in this situation. If I were to say name in this case is something that's back to Justin, for instance, and I were to do this again, now it is displayed. So and works the same as and. There is a small difference which we can get into in the next part, but for now, don't worry about it. Along with and, there is also or. I can say the pipe, which is or. So if 3 is less than 0 or 3 is greater than 2, which is a weird sort of conditional, but in this case, 3 is less than 0 is false, but 3 is greater than 0. 3 is greater than 2, which is true. The second one is true, the first one is false. This combines into false or true, which is true. I can do that, print yes. In this case, it is evaluated as true. So we can combine these statements into an if-else branch. One important thing to realize here is that if I have something like this, if 3 is greater than 4, and I'll say print hello, this is false. If I were to do an actual one, I should have probably done a better example like this. If we have no parentheses, no brackets like this, then this is fine for an if statement. The complication here is if we're trying to do an if statement. Just like in regular programming languages like C, Python, Java. Maybe not Python, definitely not Python. C or Java. I can branch together if-else statements here. So let's say A is equal to 5, B is equal to 7. If A is greater than 10, we're going to print this is true. I'm going to say that. Remember that if I were to press enter at this moment, this would get evaluated. There is no situation for me to do an else statement after this. Let me just show what that looks like. And if I were to say else if at this point, else if, let's say, B is greater than 5. In this case, this is one of the consequences of using something like R in a REPL form. This, as soon as I press the enter key on this closing bracket, the next line that executes, we see else here. It's not going to remember the previous line that was executed. So this is just a problem that R didn't really want to solve. It's not a hard problem to solve, but it's just more of a stylistic choice. That's why whenever you do if-else branches, that's why you need to have this sort of different structure. Let's say if A is greater than 10, we do print, this won't display, this is true. instead of pressing enter at this point, I have to have else on the same line as the closing brace. Else, if b is greater than 5, we're going to print the other one is actually true. And I'll close the program then. And now it prints out the second one, because in this case, a is equal to 5 and b equals 7. 5 is greater than 10. This is false, so it goes to the next one. B is greater than 5. 7 is greater than 5. That is true. So this print statement is evaluated, which is displayed to the screen. So that's just an important thing to memorize here. Whenever we have an else-if statement, it needs to continue on the same line as the closing brace. And obviously, if you have an if-else-if, there has to be some kind of structure for else as well. Let me just very quickly do something like that. If a is greater than 10, we're going to print hello. Else if b is greater than 10. So this will also be false. Print goodbye. And now we'll say else. Remember, else has to be in the same line as the closing brace. We're just going to print huh. In this case, it prints huh, because 5 is greater than 10 is false. 7 is greater than 10 is false. It goes to the last one, which is evaluated. And of course, we can nest these if statements. We can do complicated things. Any kind of standard programming language concept, it all works here. Great. So let's continue to the next thing. Next, we have this. Or I should just maybe mention this very quickly. There are more operators besides just the ones that we've seen so far. Of course, there's a standard arithmetic, like let's say 1 plus 1, that's addition, or let's do more complicated numbers. 5 plus 7 is addition, 5 minus 7, subtraction, 5 times 7, that's multiplication, 5 divided by 7, this is division. We saw earlier that when we tried to divide to when we try to get the type of a value, it was by default a double. So numbers are by default floating point values. If I were to do 5L over 7L, I wonder what this does. No, it's still like that. So it gets coerced into a double regardless. But we can do explicitly, what do we call that? Integer division by doing 5% divide percent 7, which in this case it's 5 divided by 7, and it takes the floor of that, so it removes the decimal point. So previously it was 0.7. If we remove the decimal point, it removes the 0.7 part, so it's just 0. Great. There's also a matrix multiplication operator. You don't need to know that for sure. Probably not for this course. Well, maybe for this course. It'd be cool if you did need to know multiplication. A lot of cool stuff there. But anyways, let's move on to that. You'll need that later, maybe. There's also an operator for a series and for if I wanted to check to see if something is in a set, a collection, I can say percent in percent. Don't worry about that. Next chapter. We'll see that next. Okay. Let's move on to while loops now. So if we have an if statement, then a while loop shouldn't be that complicated for a language to implement. So let's look at what a while loop looks like. First, I can initialize some kind of variable. Let's say I, or something more creative. Let's say apples. I have 5 apples. Then I can say while, we'll have our condition, just like in the if statement, while apples is greater than 0, bracket there, we're going to print paste I have apples remaining. That is going to, I messed that line up definitely. Hopefully that works. Oops. Maybe you could see my blunder here. Paste is going to combine these 3 values together. It's going to combine I have the number here, apples, and then this last string here, apples remaining. So the first iteration, I have 5 apples remaining is what it will display. This closing parenthesis here closes the starting parenthesis on the left, but it does not close the print statement. So that's why I add that in. Hopefully that won't be an error. We'll correct it if it is an error. But that's going to display that. if I were to do a closing brace right now, this program would just display this thing 1 billion trillion times just forever. Because this variable here, this apples iterator, this variable does not ever change. So let's just say I'm going to eat one apple by saying apples is equal to itself minus 1. So that is going to subtract 1 from the count. And now I'm going to close my loop. And we can see it executes just like that. So this is also where we can see why is it that we need to have a print statement here. So earlier I said that we could just say the value directly. Paste, I have apples remaining. And this line will get evaluated to a string, which gets displayed to the screen, right? We could do that, except when we are inside of some kind of conditional structure, when we're in some kind of structure of code, it is difficult for us to do that. Because if you think about it, this REPL, like I said, is going to evaluate one line of code, and it's going to print the result of that line of code. If you look at this while loop, what is the result of this while loop? This while loop is doing something, but it's not resulting in a value, which is why the R interpreter is not going to display it. So I need to have this print statement. I'll just show you what this looks like. While, let's reset this. So apples is equal to 5, while apples is greater than 0, just the same thing as before, but I am not going to say print like I said up there. I'm just going to say paste. I have apples remaining. And that looks fine to me. Then apples goes to apples minus 1 and close the while loop. And nothing gets displayed. So the REPL is trying to evaluate this while loop. It runs it, but it's trying to evaluate that to a value. Turn the while loop into a value. In this case, the while loop does not give a specific value. It puts these strings in this as a single statement, but it's not returning that to the REPL. So that's more of it's a very nuanced sort of description. I hope you can follow that, but don't worry about it. Just general rule of thumb, use print to display things. If you want to display the special characters, like the backslash characters, then be sure to use cat instead of print. But just general rule of thumb, always use print to display things. All right, so that's while loops. And again, everything I'm showing here can be displayed in more depth. I can combine while loops with if statements. I can make these large branching structures. It's all something I could do. I can also do next and break statements as well. Let's just show something like this. While apples is great, let's do this. Oranges is equal to 10. While oranges is greater than 0, I'm going to be doing something. Let's say that I only want to display something when the oranges are an even number. So you may be thinking, how do I check to see if this is an even number? I have to have some kind of conditional. I need to do some kind of fancy code. For now, I think I can probably not do a tab actually. Okay, so I can do an if statement here. The easiest way to check to see if something is an even number is by using the variable here and the modulo operator. Modulo takes the remainder of something. If you don't know how this works, just Google just programming languages modulo. This just does an integer division and it takes the remainder. So oranges divided by 2, 10 divided by 2 is equal to 5, and it divides it evenly, so there's no remainder. If it divides it evenly, if there is no remainder, then we want to, in this case, my program, I'm going to write this down here, goal, only display, we have oranges remaining when the number of oranges is an even number. So In other words, we want to skip an iteration of the loop when we have an odd number of oranges. I want to do something new when we have an odd number of oranges. In this case, we could put the print statement inside of if here. I want to demonstrate something a little more complicated here with this next keyword. You may have seen next in some programming languages, especially Java, Python, and all the standard ones, C, C++. There's this next keyword. So let's look at what that looks like. When the number of oranges is not divisible by 2, it's not evenly divisible by 2, which will only happen for odd numbers. So we're going to do some kind of thing in this if statement. In this case, I want to, oops, is this unexpected input? Maybe we couldn't have had the comment there. Let's do while oranges is greater than 0. I'm assuming that's the reason why this failed. If oranges mod 2 is equal to 1. Maybe not. Maybe we can't do unexpected input. I wish I rehearsed this part. Let's do something crazier. Okay, so let's say that we can't check to see if it's an even number. Let's just say we don't want to display new goal. I don't know why that error is. New goal. Only display we have blank oranges remaining if the number of oranges is 1 or 3 or 4 or 7 or 5 or 6. Let's do that. Okay, sort of a weird problem here. Maybe the equals sign is the thing that's wrong. Print 5 equals 5. No, okay, so equals is fine. Okay, so the weird problem here. Let's do this. So let's do our problem again. While oranges is greater than 0. This problem is intentionally convoluted, so just so we can have the practice. If oranges, we have to think about the situations this will be false. So the situations in which this will be false, the time in which we would want to skip the iteration of the loop. We are going to have some kind of code inside of this loop, and we want to skip the iterations that are false. I want to do some kind of logic if the number of oranges is equal to 1, 3, 4, or 6. I want to skip the logic if the number of oranges is not 1, 3, 4, or 6. In this situation, the oranges are initially equal to 10, so the situation in which the oranges will not be equal to 1, 3, 4, or 6 is, for instance, 2, 5, 7, 8, 9, and 10. So it's just 10 besides these numbers right here. So if the oranges is equal to 2, or oranges is equal to 5, or the oranges is equal to 7, or oranges is equal to 8, or oranges is equal to 9, or oranges is equal to 10, in those situations, I'm going to do some kind of new code here. So we are inside of the if statement here. In this situation, I'm going to say that the oranges is equal to the whatever was previously minus 1. And then I want to go to the next iteration. The next keyword will skip the rest of this while loop and just move on to the next iteration. And now I'm going to close this if statement. And now if we're at this part of the program, we know for sure that the number of oranges is not equal to 2, 5, 7, 8, 9, or 10. In this situation, we know that the number of oranges is equal to 1, 3, 4, or 6. So in that case, I want to display this new goal right here. Display we have that many oranges remaining if the number of oranges is 1, 3, 4, or 6. So in this case, very simple. Print or paste, we're gonna have to combine strings here. We have oranges remaining. That's gonna add those strings together and it's gonna print that to the screen. So you may be thinking, why don't we just end this while loop here? Just think about that for a second. We cannot do this because we have not changed the iterator value, which in this case is just oranges here. I'm going to say that oranges is equal to oranges minus 1. I need to change that iterator value, otherwise this loop is going to go back to the start of the loop and just keep running itself over and over and over again. The value of oranges will never change past 5 is the point where, or 6 is the point where it'll just keep at 6 forever if we did not have this line. Now it will, and now we can see here, if the number of oranges is 1, 3, 4, or 6, display that 1, 3, 4, or 6. We've displayed it. This problem is solved. Okay, so that's an example of the next keyword. Break, it just exits the loop entirely. But I'm sure you've seen that before. Maybe you have. So let's move on to the next thing. The next thing is the for loop. For loop is very simple. In R, it's the same thing as in Python, where there is no concept of a range-based for loop. In C, we have something like this. We have for int I is equal to 0, I is less than 10, I plus plus. This is what you have in something like C. Java does it as well, a few other languages. We have an initialization of a variable. We check a condition each iteration, and then we increment we run some kind of line of code. That's what most of these languages have, but R does not have this concept. And the same thing as in Python. What we have instead is an iterator value. We have some kind of storage container which contains a list of items, and we want to process each item in that loop. So here, I can represent the same exact thing by saying, for instance, I'll have a variable called range, which is equal to the numbers between 1 and 5, or 1 and 10, let's do for this example. This is going to be inclusive. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, including 10. This is all the values between 1 and 10, and it's now stored inside of this variable called range. We're going to see the type of this variable in the next part. Let's just see what it is, class range. This is an integer because the range stores integers. You may be thinking, why isn't this a list of integers or some kind of collection data type? Same thing if you recall about characters we saw earlier. Maybe I can find it, maybe not. Maybe I can find it, maybe not. Here it is. The class of a string is just a single character, when you should probably imply that it'll be multiple characters. But we'll see what that is in just a second. The point is, I have this variable called range, which holds a list of items. Now, I can use a for loop, similar to this for loop right here in the Java style. I'm going to say I in range. I is equal to a value inside of range, and then as soon as the loop exits, it's going to go to the next value in the range. And it's going to keep stepping up through that range until all the values are seen once. So in this case, I'm going to print the paste of iterator value, and I'm going to print out I. And that's going to be the end of the paste, end of the print, end of the loop. And now check that out. So previously with this while loop, we needed to change the value of the iterator by saying oranges goes to oranges minus 1. We're saying the value is overwritten each time. With the for loop, we are going through each value of that loop, of that collection. I don't have to put range inside of a second variable. I could do something like this. For hello in start at 4, go up to 17 inclusive. So 4, 5, 6, all the way up to 16, 17. I'm going to have brackets here, print my variable has a value of, and we'll type in hello right there. Oops, I do need to have paste to combine them. Close the parentheses right there, and now there we go. So we don't have to put that into a second variable, but just so we can see it's all stored as variables. It's all first class everything. We're gonna see what that word first class is in just a second too. But that's how a for loop works. And again, I can combine this all into inside. I can put this inside of a while loop. I can put that inside of an if statement. So yeah. One of the last things we're gonna see in this part is a function. So a function is inside of Python has the same concept. Python, you say this thing def, and then you will say some kind of keyword, like let's say my cool function, and I have some kind of variable here, like let's say my variable, and then a colon right there. And now my cool function in Python is a variable which points to some block of code, basically. And R has a similar concept, very similar concept, but instead it's a really, really cool sort of structure where we're saying, I have a variable, let's say my cool function is equal to the value of a function. And this function, let's just say it has a variable here, my variable. No colon there, but we do have a bracket there, just like as in an if statement, while loop, for loop. And now let's say I do some kind of code here. Print, paste, my variable has a value of my variable. And the bracket there. And now you can see this really cool sort of symmetry between the rest of the R programming language. We have my cool function is a variable which points to this function value, and now I can evaluate, I can run this variable in order to run this code that it stores inside. This function has a single variable that it passes in, a parameter, I should say, and so I can do this, my cool function. Just like how we do the paste function or the print function, I pass in a variable there. I'm going to say my variable is, let's say 5. So 5 is going to be set, to, my variable is going to be set to the number 5. Then it's going to run this code. In this case, if I press enter, my variable has a value of 5. If I say my cool function, let's do something more complicated. My cool function, paste, hello, world. So my variable will be set to the result of paste hello world, which will just be hello space world. So my variable will be equal to hello space world. So this is going to display my variable has a value of hello world, which it does. And we can even look at the class of my cool function. In this case, it's just stored as a function. And this allows us to have some really, really, really cool looking code. And we'll see some of that code inside of the next section, the last section. But just to keep that out there. Lots of cool stuff ahead. Okay, so that is the first part of this video. So the next part of the video is where we will go into data types. Okay, so here's the next part of the video. So previously we just talked about the very basics of the language, the syntax, the structure, some very simple commands that we can use to do some important tasks like searching a string to see if something exists, or the different data types, how we can cast between data types, the different structures like for loops, if statements, while loops. We also saw how there are only first-class functions. First-class functions is how we can is a little distinction that a function is just another type of object, just like how a string is an object and how a float is an object. So because functions are objects themselves, we can store a function inside of a variable, which has a lot of very useful purposes, which we will see in the third part. But for now, let's keep talking about some of the data structures in the second part of this video. So, to begin, the big thing about this language that I think is very interesting is that there are collection types. There's a very basic concept of a vector, and we can represent a vector with the value c. So here I'm going to create a vector with, let's say, 4 items with it. 1, 2, 3, 4. And we can see it returns this sort of list of 4 elements. I shouldn't say the word list. List is something else. So we're just going to stick to the word vector. Or you can also say collection. The term C in this case stands for concatenation. So a combination, I guess. There's a lot of different ways you can represent it. But the point is, C in this case is more of like a pseudo data structure. It's not really, there's a lot of really cool properties in R, which the first thing you should see is this, the concept of everything in R is a vector. Everything in R is a vector. If you were to look at a scalar data type, like just the number 5, right? If I were to say the length of 5, that's going to tell us that, let's say this instead. X is the number 5, and I want to look at the length of X. Length is a function that tells us how many things are inside of a vector. So this wouldn't normally make sense unless we were talking about, unless we pretended that X was a vector itself. And in R, X is a vector. It's a vector holding exactly 1 element inside of it. If I were to say Y is a vector holding 1, 2, 3, let's do something weirder. Hello world, Justin. Then we can say the length of Y is, in this case, 3. It is a vector holding 3 things. We can index this vector the same way we would index anything, like in Python, how we would have a list holding things. We use a bracket notation, so I want to get the first thing from the vector. Notice how in R, indexing starts at the index 1. Contrast that with something in Python where we would have to say Y of 0 to get hello. So this is, the 1 indexing is very elegant for like math stuff, which is what R is all about. Just remember that. Okay, so let's continue. The one thing we should also notice is that previously, in the previous part, we saw the for loop has the range notation. If we were to say like 1:5, this returns us a collection of 5 things, inclusive of the upper bound, right? So this itself is actually a vector. If we were to get the type of this, I think we can do this, class of 1 to 5. This is an integer. Well, then maybe this is a good time to talk about this as well. Like we said earlier about how everything in R is a vector, this includes things like strings, which is why we can see these types they seem to only imply a single thing, a single integer. We already saw that this vector contains 5 elements, but when we look at the class of this, it only tells us it is an integer. It doesn't tell us that it's a list of integers or a collection of integers. It only says it's 1. But we already saw that if we were to say my vector is equal to 1 to 5, and then we were to see length of my vector, this is, of course, 5 elements. It's 1, 2, 3, 4, 5. And then we were to see the class of my vector, it still implies sort of the same type as if we only had 1 element. So that's just, keep that in mind. Everything in R is a vector, even if it only holds 1 thing, which is a scalar value, which is, let's say, my value is equal to 1. Length of my value is 1. It only holds one thing. And the class of my value is numeric. I guess we can make this all, just to hammer down this point, to make this an integer type. And then we would say the class of this, now it's an integer. The integer is still the same thing as if it was a vector. So this is just a very creative thing about this language. It has a lot of elegant uses that we will see later on, but because we have everything stored as a vector, remember that in R we have, the purpose of R is to do statistical analysis. So we're going to be working with a lot of lists. So if we interpret everything in the language as a list, we can have a lot of really sort of neat programming concepts, constructs. The first thing we should maybe see is that the and versus a single and versus several ands. Don't quote me on this, but you can try this on your own. I'm pretty sure and is when you want to interpret the two Boolean arguments as a single valued, and then the and here does like an element wise anding. I don't want to get too much into it. These two are different in how they interpret the values as either vectors or scalars. A list of things or just a single thing. There's a lot of operators like that. Do we interpret it as a scalar, a element-wise operation, or do we do it as sort of like a map reduce, where we're joining a list of things down to a single element? So there's, without getting too much into it, there's a lot of cool stuff to be done there. So let's continue. Just one thing we should maybe note how 1 to 5, this returns us a concatenation. This is the same thing as doing C 1, 2, 3, 4, 5. These two things are the same. We can also do seek is a keyword, stands for sequence. Here we can say the lower bound, the upper bound, and the step. So this is just the reason why we would do that instead of the colon notation is that, let's say I want to do the items from 0 to 100, and I want to have these things, I only want to show the multiples of 10. So 0, 10, 20, 30. There's no way of representing that with a colon notation. I can't say something like that because it doesn't really understand it. So I can say seek instead to say from 0 to 100 with a step of 10. So increase each item by 10 each time. So this is just you're probably going to use something like this more than a few times. So just keep that in mind. Seek for a sequence. Okay, next thing. Let's look at, we have, so we can also, indexing inside of R is a little bit interesting. It's a little different, it definitely is different from Python. If I have something like this, I'm going to say shopping list is going to be a collection storing, let me think of eggs, milk, bread, tomato, broccoli, cereal, and let's just do one more, water. Okay, there's my shopping list. If I were to display shopping list by doing print, then it would display each of those things. Great, awesome. Just to hammer down this point, the length of my shopping list is 7. 7 items are inside of it. Great. If I wanted to retrieve the third thing from this list, so starting from 1, eggs is 1, milk is 2, bread is 3, I can say print shopping list at item 3. What if I wanted to get multiple things from this list? Well, remember that in R, everything is a vector. So 3 here is a vector. It's a vector holding one item, which is the number 3. What if we were to retrieve, instead of just 3, let's say I wanted to get bread and broccoli. Bread, broccoli, and cereal. I want to get those 3 things. And I want to retrieve that as a new vector. So let's call this a reduced shopping list. This is equal to shopping list, but I want to select only the third thing, the fifth thing, and the sixth thing. So 3, 5, and 6. Let me add some spacing just so you can see it a little clearer. I have used a vector as the index. Now I'm going to select the third thing from the list, the fifth thing, and then the sixth thing. And now, if I were to print reduced shopping list, you can see here it returns a new vector with the original items copied over. I think this is copied over. If I were to change shopping list at item 3 from bread, if I were to change that to grains, and then if I were to print reduced shopping list, yeah, so it is copied over. It's not a reference, which is interesting. Okay, that's probably very slow for some cases, but it's very good for other cases. Okay, let's continue. So now this notation that we're seeing here, where we're indexing, you can see I can change the item from the list, all this fun stuff. This is something that applies to all the data types we're going to see, at least the basic data types. So it's good to keep this sort of structure in mind. I can also remember that here I can set a single item in this we can reset it to grains in this case. You can also notice the symmetry here. I am able to retrieve multiple items if we use the index as a vector. So, what if we were to say shopping list from C 1, 3, 5, let's see, 1, 3, 5. That is equal to not available. That's actually a reserved thing. Let's say I don't remember. So I don't know, my shopping list got corrupted. So let's assume that. Now if we were to print our shopping list, we see at item 1 is I don't remember, 2 is milk, 3 is I don't remember, 4 is tomato, 5 is I don't remember, 6 is cereal, and 7 is water. So we can set multiple items all at once, which is it's a very interesting symmetry in the language. There's a few uses for this, so there's a lot of cool stuff we can do. Okay, now let's move on. So this is one thing you may need to, I keep trying to type clear. There is no clear command in this language. So that's a Linux thing. We can repeat items. This is just an interesting thing that you can maybe look at. There's a few uses for this as well. I keep saying that, but there's a lot of uses for everything I'm saying. Rep is short for repetition. It's just a method of getting lots of... you realize that your list contains the same thing over and over again. Let's say I want to have the goal here, create a list of 10 things all set to 0, right? If I want to do that, that's similar to saying I want a repetition of 0 times equals 10. I want that thing 10 times. Okay, what if I wanted to do a list of 10 things alternating between 0, 1, 2, 0, 1, 2, 3, 4. Let's start this at 1. So 1, 2, 3, 4, 5. So I want to have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. There's 10 things in this list. Okay, so this is similar to saying I want a vector, which is 1, 2, 3, 4, 5. I want to repeat this 2 times. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. So what if I wanted to do this? Let's see if we can do this. I'm going to open up some kind of paint tool. Here we are. Hopefully this is at all visible. We're just going to put this right here, I guess. Let's say, instead of repeating the list like that, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's one way we could have repeated the list. And we could see here, if we read this memory from the top left to the bottom right, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that's how we get this. There's another way we can interpret this data, and it's what if we did it like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now if we were to read this from the top left to the bottom right, we have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. What if we wanted to repeat our list this way? Well, we can still use rep, see 1, 2, 3, 4, 5. Instead of times, we say each. Each is it's just a different, times you can imagine is horizontal, each is vertical, I guess, if you want to imagine it that way. But this is how we get that new sort of list. All right, great. So that is the repetition. That is there it is. Okay, one more thing to say is that a vector, which is what we've been talking about so far with this C stands for concatenation, a vector only contains the same data type. So we can't say, I don't know if this will give an error. Maybe this will not give an error. Hello, 1. Well, this is actually, okay, so it didn't give an error, but I did give this thing. Let's call this list my new concat, which is C of hello and 1. And then I were to find the class of my new concat. This is a character. Okay, so we can see this is why this is. Notice the quotes around the 1. The type of this 1, I just said that the vectors must all contain the same data type. So this 1 had to match hello. We have to turn 1 into a character type, or else we can't represent this all with the same data type. So that is, if you were to try and say, let's say x is, I haven't tried this before. Let's see if this is my new concat of 2. X is now equal to the number 1 because we're getting the second thing from that list. And then we were to print out x. This is a string that. What if I were to do y is equal to x plus 7? And this is, okay, so this is something that we would maybe need to think about then. So this is a very possible error you may run into. Here, I initialize the vector with a number. But here, I retrieve that number and try to add it with another number. If you don't remember that vectors must all contain the same data type, you may think that this should work. But this is the sort of secret, deadly killer right here. It's like, if you don't remember that the types are, what's the term I'm looking for? The types change. It's implicitly changed without you really commanding it to. Then this could be a source for errors. Okay, what if I needed to reserve the types though? That is for the list. The list can contain multiple types of items to it. A list can also allow you to append stuff to a collection. I'm not sure if this is possible. If we were to say my vector is equivalent to C of 1, 2, 3, and I were to append my vector 4, does this work? I don't know if this is the same vector. I don't know. We'll see. There's probably nuances here. But a list does allow you to append stuff to it. We just saw vectors do as well. I'm not sure what the difference is. This may be like a performance thing. I wonder if it's creating a new vector versus allocating more space into it. Who knows? Do you test on your own? Have a little R shell next to you so you can see what the performances of this stuff is. That might be a fun project to do. Okay, so let's continue here. A list can be initialized just by doing this. Instead of saying my vector is equal to C, like we just did up here, we can say my list is equal to list 1, 2, 3. Let's just keep at the same way. Now check this out. Type of my list. Oh, I meant to say class or type of. So my vector here was initialized as a vector, class of my vector. And that had the type of numeric, because in other words, you can imagine it as the type of the data being stored. But for a list is something discrete. It's different. A list has a type of list. So it's like the type is being lost, kind of. The class of the object, it's more familiar to what you would see in Python, I think. The class of the object is the type of value it actually is. This is a consequence of R treating everything like a vector, but it's a little interesting. Okay, so the lists we just saw are stored as a list. That is their actual type. And we already saw also that we can append stuff to lists. This is how we can do that. So I want to print out my list. It's that. I can append stuff by just saying my list is equal to the appending of my list to, let's say I want to add in 9. And then I were to print out my list again. Now we have 1, 2, 3, 9. So that is how we can add stuff to our list. What if I wanted to add stuff at a specific part? So then I can say my list is equal to append my list. I want to append the number 7 after, let's say I wanted to make this list say 1, 2, 7, 3, 9. So I want to append 7 after the index of 2. After the index of 2, and I can print out my list, which is 1, 2, 7, 3, 9, like we just said. We can also do, there's more cool things that we can do with this. Let's say I want to check if, or let's just print out this. I want to print out, is 7 in my list? True. Notice this operator right here. This is actually the entire operator. This may look strange. I thought this looked strange too. Like, why not just say in without the percent signs? I don't really know. It's similar to integer division, how integer division is percent divide percent. It looks strange, yeah, but that's just how it is. So if you want to see if a value is inside of a list or a vector or a matrix or something, just say percent in percent. So here we can say if 10% in percent my list, then we can say print present, else print missing. And there it is. 10 is not inside of my list because it only contains 1, 2, 7, 3, 9, so it would be print missing. Great. I think that's all the things with lists, really. There's more stuff, but we can skip a lot. I recommend having this stored inside of, have the documentation for R open when you program, because there's a lot of really small details that you may miss if you don't do a lot of programming. Oh, one thing I could mention is that negative indexing. So we saw earlier that you can index with a collection, basically. So let me just make some room. Print my list. Everything I'm about to show you also works with vectors. It also works with matrices and everything else. So we're going to get to matrices in just a second. But lists, vectors, matrices, data frames also, we'll see in just a second. But the point is, if we were to print out my list, we can see it contains these 5 items, 1, 2, 7, 3, and 9. If I wanted to select 2 and 3 here, 2 and 3 are located at index 2 and index 4. So, like you saw before, I want to print my list C at index 2 and index 4. And this gives me those 2 things. What if I did not want to select those 2? I want to select everything besides those 2. Well, all I need to do is make those things negative. I want to get everything besides 2 and everything besides 4. So now this gives me index 1, index 3, and index 5, which is 179, 179 down there. So that's really interesting, which is also why it's a big source of errors for people, because they'll be like, I want to get the last thing from the list. So they'll do the Python method where they'll say -1, and -1 will give you everything except for the first thing in the list. So that's the first sort of source of error I think people run into. Okay, so now let's move on to... We can maybe see this as well. We can join together lists and we can subtract stuff to it. If I were to join two lists, remember that vector types start with C. Okay, this is a vector. 1, 9, 7, 6, 3. This is a vector of stuff. If I have two lists here, like list 1 is equal to a list storing hello, world, and then list 2 is a list storing 1, 2, 3. I can join these lists together into a brand new list, list 3, which is equal to the concatenation of list 1 and list 2. And if we were to print this out, hello world 1, 2, 3. And these types, the types of those objects are preserved. They're not, this 1, 2, 3 is not turned into a string like we saw before with the vector type. So that's a very cool thing about this language. We can just combine things very easily. We can also subtract things as well. If we wanted to remove stuff from this list, it's as simple as index. Let's say I want to remove 2 from this list. So very simple. 2 is located at index 4 of this list, of list 3. So if I want to say list 4 or list 3, I want to remove the item right here, item at index 4. This is just equal to list 3, everything except item 4. And there we go. So removing from a list is as simple as just selecting everything besides that index. All right, so now let's move on to matrices. So a matrix is it's a two-dimensional ordering of rows and columns. So it's similar to this example I just showed here, but pretty different actually. Well, let's not do that. Can I just draw like, how do I do this? I'll just do this. There we go, perfect. A matrix is a two-dimensional ordering of rows and columns. We're going to get into, so previously lists and vectors are all one-dimensional. They increase from left to right. In memory, they go from a spot of low memory to high memory. There's no concept of dimensionality. So a vector is slightly different, a matrix is slightly different because they do have this concept of multiple dimensions. Later on, we're going to see a data type that has in dimension. So it does not have just 1 or 2. It can have 3, 4, 5, 6, any sort of dimension. So you may be thinking, why do we have a matrix type that is distinct from that? Why do we have a matrix type which is only a dimension of 2 versus a super type, let's just say array, which is the actual name of the dimensionality, the actual name of the data structure with that can be n-dimensional. This can be dimension of 1, 2, 3, all the way up to, I don't know, infinity or something. You probably can't have infinity, but so you may be thinking, this is what I thought as well. Why is it that we have this matrix data type at all, which only has 2 dimensions? Isn't that kind of restrictive? Why don't we just have this and only this? Why is array different from list as well? Well, we're going to see those and more, but the big idea is that if we have a data type that represents data in only 2 dimensions, then we can have a lot of really elegant math operations that are already well defined in all of these math textbooks and everything, right? All throughout history, people have been making sort of algorithms that work with matrices, ways to transform the data and make it into something new. So if we were to allow the programmer to define matrix-oriented data, we can do a lot of transformations on that. So arrays are more for storage. Matrices are more for transforming the data, changing it into something brand new. So, oops, I shouldn't remove that. Well, that'll be our problem in just a second. Okay, so a matrix. We can make a matrix just by saying, we'll call this matrix, hello matrix. Matrices are only two-dimensional, so we don't have to worry about defining different kinds of dimensionality. So we can say the matrix is equal to this data type matrix, just like we did with list before. We just said list and then the arguments. Here, we have the arguments be a vector. So I'm going to say my matrix elements are all the items 1, 2, 3, 4, 5, 6, 7, 8. So then we say the number of rows in the columns that our matrix has. Rows go from left to right, columns go from up and down. So if I wanted my matrix to be like row 1, which is 1, 2, 3, 4, and then row 2, which is 5, 6, 7, 8. That's what I want my matrix to look like. Then we would have in row, there are 2 rows, and in col is equal to 4. There are 4 columns. If I were to print out hello matrix, then it looks just like how I just described it. Or in this case, it's actually oriented a little bit differently. We can see 1, 2, 3, 4, 5, 6, 7, 8. I think we can change that just by, we can transpose it, or we can do what the repetition we did before is. You see, before we said rep each and times. We could just do that differently. But anyways, I'm pretty sure there's a transpose argument here, but I don't want to look it up right now. So matrices are just two-dimensionally oriented. We saw previously in the previous part that there is a matrix multiply argument here, percent times percent. So it is already built into the language that we have support for matrix operations. There's also other ones like skew, transform, translate. There's different operations on matrices. Okay, so we can get the dimensions of the matrix just by getting dim. This is a new command. Dim of hello matrix is 2 by 4. Notice how this is a vector data type. So it's the same rules apply for all vectors. 2 by 4 matches the rows and columns that we specified here. All right. Now, another thing. We can access the items from the matrix with a similar notation as C# does. I think, Java does not do it. I know for sure C# does it this way. Maybe Python does it this way as well. TensorFlow does it. If we were to have a matrix here, hello matrix, and I want to get, in this thing, the item located at row 1, column 3. So I would just say 1, comma 3. And this returns us 5. The thing at row 1, column 3 is 5. What if, though, I wanted to get everything in column 3? So in this case, everything in column 3 would be the numbers 5 and the number 6. In that situation, the row index is 1 and 2. So I can say C, 1 and 2, comma, and then column 3. And that gives us 5 and 6. Another way of writing the same thing is by saying hello matrix, C, instead of putting anything inside this first square, this first spot, where we say, in this case, previously I said I want every index, every row. I'll just put an empty spot there. You can move the space there. The spaces are arbitrary, but put a comma there, and then I want to say read row or column 3. And you can see these two things are equivalent. We can either use explicitly denote the indices that we want, or we can pass in a comma there just to select everything. And like I said previously, what if I want every column except for column 3? So I can say I want hello matrix every row except for the column 3. Everything in the matrix except for column 3. Bam. So 1, 3, 7, 2, 4, 8. So the negative notation works just fine. It's great. Okay, you can add stuff to the matrix by saying C bind and R bind, column bind and row bind. So let's say here my hello matrix, it currently contains, let's just type it out again. Hello matrix. Everything we just showed, I didn't modify the original matrix. So the original matrix is still set to what it originally was. So here, I have my hello matrix and it has these 8 items into it. Let's say I wanted to add a new column at the very end. So I can say hello matrix is equivalent to C bind. I am adding a new column to hello matrix. The column, it can only contain 2 items. Note that, because if I added more columns to it, then we would have to also add a row as well. So we only want to add a new column here. The column we're going to add is 1, 3, 5, 7. Let's just do 99 and 100. Just something arbitrary like that. And now, if we were to display this, check that out. We've added a new column. If I wanted to add a new row here, I can say R bind. Hello matrix is equal to R bind. It's equal to hello matrix. And in this case, we have to add 5 items. A new row would be 5 items long. So here I can just simply do, I don't know, 10, 11, 12, 13, 14. There we go. New row added. Great. If I wanted to get the dimension of this matrix, I could just do previously. We already showed that. Just dim hello matrix. 3, 5. So it updates. Cool. Oh, if we wanted to get individual, I don't know why you would want to do this as opposed to just getting dim, but I mean, it could probably just, they added a lot of keywords here. In rows, hello matrix. This just gets us the first thing there. In row here is equivalent to just saying dim that at index 1. It's just, I guess, his personal preference, whichever you prefer. So now let's move on to the array. An array is something that, so matrices can only contain one data type, like we showed before. It's different from a list, which can contain arbitrary data types. Arrays can also contain only one data type. So we've previously discussed vectors. We've discussed lists. We've discussed arrays. And we've discussed matrices. And now we're doing arrays. Okay. An array is like a list, but it can contain 2 things. 1, arbitrary dimensions. Lists were only one-dimensional. You cannot have, and what I mean by dimension is how many commas are in this index field. Is there only 1 comma in the index field? Does it go in left, right, and up and down, or does it go left, right, up, down, and forwards and backwards? Or multiple like that? Can we have a 10-dimensional data type? 100-dimensional? It's all possible with arrays. But with lists, you can only have 1 dimension. Vectors are the same way. Matrices are only 2-dimensional. Arrays can be 1, 2, 3, 4, all the way up. But arrays also contain still the same data type. So if I put a string in there and an integer, the integer gets coerced, that's the term I'm looking for. the integer gets coerced into a string. So let's go ahead and create an array by saying my cool array is equal to array from items 1 through 24. So let me just stick to this. See 4, 5, 6, 7, 8, 9. How do I do this? 4, 5, 6, 7, 8, 9. I want to make this less trivial. 12, 13, 14. Okay, so this would be 16 elements in this array. I want to make this have a dimensionality of 16. This would be a vector, so I need to put the C on top. Okay, if I were to do this right now, then my cool array contains only one thing. My dimensionality had a single dimension specified, which that single dimension had a length of 16. So it's one dimensional. If I were to say dim of my cool array, this has 16. So that's not very creative. Let's say I wanted to make this array, instead of having 16 items in one dimension, it was 8 by 2 dimensioned. So the dim changes from 16 now to 8 by 2. And now if I were to print that out, check that out. 8 rows, 2 columns. What if I wanted it to be something even crazier? So instead of 8 by 2, it's 4 by 2 by 2. I think that 4 and 2 is 8. Yeah, so that would still work out good. And now if I were to print out the dimension, it's still the same thing. And if I were to print out the actual array, it looks weird. It looks crazy. But you can see the commas here are very specially placed. So is a comma before, after, or is it multiple before? Things like that. All right, so arrays are multidimensional. Still only one data type though. I'm not sure what would happen if I appending would take too much work. If you appended a string to this, would everything get turned into a string? Probably it would, but you can try that out on your own. The last data type to talk about here is I guess there's two more. The second and last one is the data frame. So if you've done anything in Python, pandas, then you know what a data frame is. A data frame, to put simply, is, let me erase this. Let me fill this in with a color as well. Bam. Okay, great. A data frame is a collection of terms. It's a collection of symbols with associated values. That's probably not very helpful. A data frame, let's just call this DF, contains a list of rows, a list of columns, I should say. I'll say age, I'll say name, and money. The point is that each of these columns have their own data type, and we have different rows, and each row needs to be filled, basically, with an associated value from each of these. That value can be null, or it can be an actual value. So age is null, I guess, here, but name can be Justin. Excuse my handwriting, I'm writing this with a mouse. Money, let's say I have $20. I shouldn't put the dollar sign there, it's all numeric in this case. 20. Then I have age, which is 30. A 30-year-old named Sophie. And the money is $1 million. So, and so on and so forth. So a data frame is like a matrix, but each column of the matrix has its own data type. Data frames are mainly used for storage again, but it's very easy to represent things like CSV files as a data frame. Very easy to load CSV files and operate on them. So that's how they are distinct from matrices. Matrices are mainly used for transformation, changing the data in some way. So to create a data frame, very simple. We just use this, let's say my awesome data frame is equal to data.frame. And I can put this on different lines as well, just to make this a little bit easier. But let's say that I have let's just represent this example we just did. So we have age, name, and money. Age is our first thing here. And we're going to say age is equal to a collection of numbers. Let's say there's 10, 20, and 30. That's our first field in this list. The name is the second field, which is going to be Justin, Emily, and Sophie. Just 3 names I'm making up. And the final thing, which we will say is money in that previous example, money is going to be more integers. Let's say that Justin has $20, Emily has $100, and Sophie $1 million. Excellent work, Sophie. And we can end the data frame with a new parentheses. And now if we were to print out my awesome data frame, check that out. We've got things there. Sophie's rolling in the money. So we've got lots of scientific notation, lots of decimal points there. So data frames, if you've worked with Pandas before, and I'm definitely pronouncing that incorrectly, pandas, then you're probably familiar with how to work with these. It's just a neat little storage mechanism. If I wanted to summarize this is a cool feature. I want to get a summary of my awesome data frame. Check that out. Oh, this is kind of hard to look at, but depending on the types of each column in your data frame, if it's meant to store numbers, then we have this sort of numeric summary that stores the quartiles, the minimum, first quartile, median, mean, third quartile, and the maximum item. For age, it probably wouldn't make that much sense. Well, maybe it would if we had a lot of things here. Money maybe as well. For the name, we have not really anything helpful because that's a string. It's hard to summarize strings, I bet. But for numeric entries, this summary would actually be very helpful. So if you wanted to very quickly get a summary of a very, very big sort of data set and you just want to see like, what's the standard deviation or whatever, check out the summary item. Okay. So the final thing we have to talk about here is a factor. Or let's do this as well. I've skipped over this part. Last thing about data frames. We can access the indices of data frames in 3 different ways. The first thing is, let's say I want to get all the names. I want to get every name of this data frame. I can say print my awesome data frame. I want to get the things at the name field, which is at index 2. Age is index 1, name is index 2, money is index 3. So index 2, bam, those 3 things. Note that this notation gives us a brand new data frame. This is a data frame with the field called name, and it has 3 things inside of it. What if we were to access it with this other notation? Print my awesome data frame, bracket, and then the name of the field you want to access. In this case, I shouldn't have, probably a little confusing. I want to access the name field. So we pass in a string inside of brackets. And now that just gives us each item inside that column as a vector. The final thing is a little weird notation. I haven't seen this before, but maybe some of you have. I'm not sure why you would want to do this as opposed to the other 2. But you can say my awesome data frame, $, and the name of a field. And it gives us the same thing as this thing before. I'm sure that's related to Bash or something. Or maybe Perl. I think Perl does something similar to that, but I don't really know. Okay. And finally, rbind and cbind, as we saw with matrices, it works the same way with data frames. So we can add new rows and columns with rbind and cbind. Okay. Last thing to talk about with the last data structure that you should probably remember is a factor. A factor is kind of like if we were to combine a list with a set. So if you remember from data structures or a hash set or something like that, with data structures, a set is a collection of items where there are only unique values. It's an unordered collection of unique values. So if I were to have a set with the values 1, 5, 1, 1, 1, 5, 7, 1, 5, this would be equivalent to a set containing 7, 5, 1. Unordered, no particular ordering. I could say this is the same as saying this, I'll say equals equals. This is also the same as saying set of 5, 1, 7. So that is something like in Java, for instance, that's a true statement. This language, R, does not have any kind of set. It does have a factor, though. So let's see what a factor is. A factor can be created by first defining, let's say, my collection. I'll keep the naming scheme we have in my sweet collection. This is equal to a vector, which contains our items. Let's just say 1, 5, 1, 1, 1, 5, 7, 1, 5. I should not have put that as a string there. It's not a string. Okay, so this is just a vector, regular vector we've seen so far, nothing new here. If I were to make a factor out of this, then I can say my fun factor. This is equal to a factor on my sweet collection. So we have our factor, we pass in a vector into the factor as an argument. And now, check this out, print my fun factor. This has the original vector, and it contains this thing called levels. Levels is essentially the set that I was saying before. It is an unordered collection of the unique items. Factors are very good for categorizing data. I want to summarize data. I want to categorize it into different unique sets. There's a lot of cool operations on factors that we won't get into because this is already a very long video. Oh my goodness. There's still one more part to this. I don't know how I managed to get this video so long. So yes. What if, though, we wanted to do something like this? Imagine that we have a factor here defined, and we want to make it so the number 5 is not allowed. I can define my own levels. So the levels is like the set of, let's pretend that levels is a set of allowed items. If I wanted to remove the number 5 here and make it so that is no longer allowed, let's say that my fun factor is instead a factor with my sweet collection, just as we've done before, but let's say that the levels, which is a named argument, is equal to only 1 and 7. Those are the only allowed items inside this factor. And now if we were to print that out, check out what happens. We have said that anything that is not 1 and 7 is now not allowed, does not exist. So that's a very interesting way of categorizing our data, basically. If we were to change the items in this factor, so let's say I want to change my fun factor, I want to change this item there, which is at index 1, 2, 3, 4, 5, 6. At index 6, I want to change that to something that is inside of our levels. So let's change that to 7. Now that 7 has, that not allowed has changed to a 7, which is great. But what if I were to do the same thing to index 1, 2? So index 2, I want to change it to something that is not in our factor. So let's change that to 9. 9 is not in our levels. We get this scary warning, and if we were printed out, nothing's changed. Let's do the same thing with something that looks like an actual change. 3. So I changed index 3 to 9. 9 is not in our levels. It doesn't get updated. So does not exist still. So that's levels. That's the last data structure you'll need to know for the most part. There's others, but we can, for now, this is a good jumping off point. Okay, so this is the last part of the video. Now we're going to be talking about a few of the graphical applications of R. So remember that the main purpose of R is for statistical classification of programs. So you have a data set and you want to create some kind of graphs and depictions of the data of that data set. So you analyze different trends of it, you draw trend lines, bar graphs, pie charts, histograms, all that stuff. So here we're going to be drawing a few of those graphs, basically, and seeing what that looks like. So first off, just to make things easier, and also to show a few of the cool things about this language, I decided to make this function here. So let me make some room here. This function is called fmap, and it's my own function I'm creating right now. So we can create a function the same way we've been doing in the first part, where we say a variable, we're assigning it a value of a function. Here we're passing in two values, an input called x and a function called f. And here the idea is that I want to have a vector x, which has either one value or many values, or maybe even zero values. But the point is, each of those values in the function, each of those values in the vector, gets applied to the function, and then they get set to a result. So it's mapping the function to the value, or vice versa, I guess. So here I'm going to be initializing a vector called y, which has a length equal to the length of x. Then, for each value inside of the input vector, so I in 1 to the length of x, for each value in the input of the vector, we are saying that the output value is equal to f of the input value. So we're applying the input function to the value x. And then finally, we can just return y. So I didn't show this return part before, but basically it's just the same as in Python or C or anything like that. We have a function, the function calculates some result, and then we can replace the invocation of the function with whatever value is returned. Here's a little simple example that we can show just really quick. I can say ages is equal to a list like this, or a vector like this, 10, 8, 13, and 17. So 4 items in this ages list, ages vector. And then we can say ages is equal to, or let's make a new function here. Let's call this function increment ages is a function that when given an input value age, what it should do is it should return age plus 1. And this needs parentheses. If the parentheses are not included, then that will result in an error. Just like that. So now this increment ages, all it does is that when you put in a value, it returns the value plus 1. Now I can use my fancy fmap function to say that the ages list, if we print out the value right now, 10, 8, 13, 17, the goal is that we want to increment each of the ages inside of this list just by doing each of those values plus 1. So by using our new function, our fmap function, and our increment ages function, we can say that the ages vector is equal to the map of the ages vector to the increment ages function. So each value in that vector will get applied to the function, and then it will set that into a new vector. And now when we print that out, notice how all the ages are added by 1. And if we run this function 3 more times, for instance, we can see that now all the ages are plus 3. So using this method, we can represent the idea of, this is a good representation of first-class functions. Because functions are stored in an object in the same way that other objects store data, we can pass functions as values into other functions. We can pass them as parameters, which makes for really nice looking code. So this program is about, what I'm going to be demonstrating now is about making graphics that depict different data sets. So here, let's create just an example function. I'll call this f quadratic. And what f quadratic will do is that it is equal to a function with an input called x. And this is going to represent a quadratic equation. So a quadratic equation has x be squared, and then it has a potential offset to there. And so we can just make up a random equation. The one I'll do is x minus 5 squared. Notice how this language has powers be represented as the caret. Unlike Python, which has times, this one has the caret. Minus 10. So just a random function. This is arbitrary. The point is that we have some kind of function that represents data. The easiest way we can make a plot is by first defining an input domain. So I'll say x values is equal to the values between 1 and 10. And then y values, this is where we can use our function as earlier, f map the x values to the quadratic function. Notice here I could very easily have just made this a for loop myself, but just to demonstrate this fmap idea and to save a lot of really repetitive code, I just thought this would be nicer to do. So now y values are the application of the f quadratic function to each input value x. And the easiest way we can display this result is just by plotting the y values. So nothing else special about it. We are just displaying the y values itself. Only one parameter. And so what this program will do is that R is going to guess what each of the x values are corresponding to each of the y values. It's going to say the first point you put in has an x value of 1. The second point you put in has an x value of 2. The third value has an x value of 3, all the way up. In this case, it works out pretty conveniently because that's what the input actually had. But this would be messed up if we had an x value set of something other than 1 through 10. But if you just have a set of just random data points and you just want to quickly see the trend line, then this will be very easy to do. Just plot those values. So that is a very simple dot plot. So let's look at something more complicated. Here, I'm going to make a sine function, which is just going to return the sine of x. So it's going to look like a wave, sort of. If we wanted a nicer looking graph, I'll go through each of the main sort of graph utilities that that you'll probably be doing a little bit of stuff with for this class. So again, the x values are just some domain I'll pick. Like let's say -5, -4, -3, all the way up to +5. So 10 points. And then we can say the x values are the mapping of, the y values are the mapping of the x values to the sine function. So now the y values represent the sine wave, basically. After that, we can plot this, and now let's look at all the different variables. So first off, there is for the plot function, we first pass in the x values. Earlier, we assumed that the x values were nothing important. If you only pass in one parameter, the program will just assume you're only passing in the y values, and it will guess the x values for you. If you do pass in those parameters, you can pass in an x and a y. So here I'm going to be passing in the x and the y. And now the next thing we can type in is the next thing we can use as a parameter is the type. The type, there's a bunch of different types. I think there's 6 normal ones, and they describe things like how the dots are depicted. If we do p, which is a string here, p represents just random discrete points. If we do O, then what this does is that I think it draws the discrete points, but it connects them with a line. So this is where we can draw a line graph, basically. And it's if you just ended the equation right here, let's actually look what this looks like. Here it is, very simple. So each point in our set is a circle, and we're connecting them with lines, basically. And this is our sine wave, essentially. So very easy to do. Let's do the same thing, but let's add in more stuff here. So plot x, y, type equals O. And now our next parameter here, main, is a way for us to set the title of the graph, basically. So we can say my cool graph, my cool line graph. Then we can set the x and the y labels, the labels for the different x and the y axis. So we can say x lab is equal to, let's just say, my x domain. Y lab is equal to my function applied, and we'll say this is sine x. Just completely arbitrary, I'm making this up. We can set the color of the line itself. In this case, I'll just say the color is equal to red. Notice how this is a string. We can set it to an RBG value if we want to do it programmatically. So right now we can just look at it as a string. So it's very convenient as a string. Then we have the CEX value. CEX stands for character expansion, and it's the size of each point relative to 1 equals normal. So if we set this to 1, then nothing would change. It would look exactly like I just showed it before. If we make it 2, then each of those points will be 2 times bigger. If we make them 0.5, then they'll be half as big. So here I want the points to be bigger, so I'll just say 2. Then we have PCH. In this case, I'll say that's 25. PCH stands for plot character, and it's the size of the, I think this is the size of the, well, I don't know why I had PCH and CEX. We can test that out in just a second. Plot character, the size, I think this PCH is the size of the text. We'll see. We'll do both. Then there's LWD. LWD is the line width. So I like to do thicker lines if it's a dotted graph, which this one isn't, but in the future we'll see them. So again, it follows the same rules. 2 equals 2 times bigger, for example. And then we have LTY, which is the line type. Oh, this is where we do actually have dotted lines. So this is where you should look up, oh, I remember what PCH is. Plot character, the type of symbol to display. If you were to Google R, you're gonna see with these plots, there's a list of different plots that you can make, and this PCH and LTY, they correspond to a table which describes the actual symbols to use. For PCH equals 25, I think this looks like a circle with a plus sign inside of it, or maybe it's a little different. But if you were to Google this, you'll see a table that says, oh, PCH equals 1 is a dot, PCH equals 2 is a triangle, etc. Same thing for LTY. Here, LTY of 6, I think, is a dotted line. And that's all the parameters you'll probably need to work with. So there's a lot of customization here. But check this out. So we've increased the thickness of the line to double size. So in this case, PCH equals 25, that corresponds to a sort of triangle. So we can see what if we were to change this. Oh, it's a lot of typing actually. Plot x, y. Let's just do PCH is equal to 24 instead of 25. now it's upwards facing triangles instead of downwards facing triangles. So instead of PCH, let's mess with LTY. Instead of 6, let's make that 30. I guess it's invisible now. If we say LTY equals 4, or this may be involved in some other variable instead of PCH. Oh, I see. This has to do with the type, which must also be O. There we go. The type determines the if it's a dot plot or if it's a line plot. So we have to, it's initially a dot plot, which has no lines connecting them. So we make it O, then now it's a line plot. And LTY equals 4, that was this sort of dotted looking line. Okay, so that is the dot plot. What if we wanted to display multiple lines in our graph? So that would be very simple. All we need to do is we note this plot function here. You can imagine it as creating a brand new graph, and then you can add stuff to that graph after you create it. And all that stuff will be added to the graph until the next time plot is called. I haven't tested this out in the REPL yet, so if this doesn't work in the REPL, then we can see what it looks like together if we just run the function itself. So let's look at this. First, I'll just find a new function here, just as it's done before. Tangent, which is a function on a variable called x. The tangent of an angle in radians is equal to the sine over cosine. If the cosine is 0, then that would be sine divided by 0, which would be an error. We don't want that to happen. So we can do this nice little ternary operator here. A lot of languages have a concept of a ternary operator. I think Lua does have one, but it's also weird. It's a way to evaluate an if statement in a single line. So we can say if the cosine is equal to 0, then we'll return infinity. Notice how it's its own sort of keyword here, INF. Else, we return the sine over cosine. I guess we can reuse, instead of cosine x, we just reuse c. And then, now we can test it out. F tan of 3.14. 3.14 is a sine of almost 0 and a cosine of almost -1. So 0 over -1 is going to be close to that number, right? Just to spice this up a little bit, we can say a tan 2 as well. Or sorry, not a tan 2, just regular a tan. So a tan stands for inverse tangent. It's just another function we can do just to make things more interesting. In this case, all this is, the inverse tangent is 1 over the tangent of an input variable x. So we can see f a tan of 3.14 is the inverse of 0.00159. So now that we have two different functions, let's define a single input domain. In this case, I want to have a smoother looking graph. You saw the previous graph, which was supposed to be a sine wave. It had each value that was input was very large values compared to radians. It was -5, -4, -3. Notice how each of those values, they step up in differences, in increments of 1. And remember, radians, they only go from 0 to 3.14. So it's if you only have 3 points in that range, then it's not going to look like a smooth graph. So if I wanted to have a smoother graph, let's just do the sequence of 0 to 3.14 with an increment of 0.1. So this is going to give us 314 points, and it's going to show us a very smooth looking graph in this domain. If you wanted to, you can even make this increment even smaller, or you can change 3.14 to 6.28 and show the entire area, the entire range of these two functions. But these are the x values. We have two different y values to display against each other. Both of them will use the same x values. But here, let's say that y1 is the mapping of x to the tangent function. y2 is the mapping of x to the atan function, the inverse tangent function. And now let's display this. The way we display this is by first running plot on the first graph, x, y1. Let's just make up some other variables here. Everything is coming from the left side if you're seeing that. So let's make this a line graph. So we have L to signify that. Previously, O signified a line graph, but we're putting dots on each point that we inputted. So if we do L, it's just the lines, no points are shown. So let's say that the color of this first one is blue, the tan function. The x lab is radians, since that's what in this situation, in this context, it makes the most sense for it to be in radians. The y label is the function applied to input. The LTY is the line type. So I want this to be a full line. So that would be 1. So that's a dotted line would probably be 2 or 3. We saw that before. And then we have the line width, which is 1. And if we display this, this is just, check this out. So this is the tangent function. The actual tangent function does not have this line in the middle. There's ways you can correct that, but that's takes a little bit more effort. So we're not going to look at that. But this is just a nice little representation of our first graph. So the point of this, though, is that we want to have both graphs displayed on the same image. We can do that by then calling this lines function. Remember that I said plot, the goal of it is to rewrite itself, basically. I don't want to rewrite ourselves. I just want to have a new sort of line drawn on top of the same image we just did. I don't know how this will work, but let's just try it out. So I'm going to do the same thing. I'm going to say draw y2 with the same x values, a type of L. We're going to do a new color. We do not need to set the x label or the y label. We can just keep those the same. And we're going to say the line type is something different. Previously it was 1, now let's just set it to 2. And similarly, let's set the line width to 2 as well. Plot.new has not been called yet. Maybe we have to do this. This is what I was kind of worried about. There we go. Okay, so instead of closing this program, you just keep it open. And now check that out. So we have both plots displayed on the same image, which is pretty cool. Okay, so we can also add on a legend to this image. A legend is just displays what each line represents. So the legend that we're going to do is just in the bottom right corner right here, just something that displays that the blue represents the tangent function, the red represents the atangent, inverse tangent function. So let's create a legend. X, the position of the legend is going to be in the bottom left, or let's say bottom right, just to be consistent to what I just said. It's going to be located in the bottom right. The inset is 0.05. The inset is how many x points we are located from the edge. So 0.05 would be a tenth of the difference between this area. So it's going to be located like a very small. We don't want this to be 0 because then the legend is flush with the edge of the graph. So we set it just a little bit to the left, a little bit up. Then it's like padding. Then we can say the legend itself has, what are the labels for the legends? We want to make this a vector, so it's like an array, it's like a list, we're storing multiple values. Here, the legend will be tan is the first line, that we plotted, and atan is the second line that we plotted. These names can be completely arbitrary. So let me just make this even more different. So tan x, atan x. So that's the text that will be displayed. Next, we have the color of the different lines. The first line is blue, the second line is red. So blue, red. Then we have LTY, line type. The first line has a type of 1, the second line has a type of 2. And finally, the line width. The first line has a width of 1, the second line has a width of 2. So we're just copying the values that I showed earlier in the earlier plot. We're just the plot and the lines, we're just doing those again. And that's everything. And check that out. We have a nice little inset sort of legend here that displays that the blue line, the blue solid line, is tan x, and the red dotted line is atan x. And of course, you don't have to use a function for these. You can make it read from a CSV file and display everything from there. Okay. So what if instead of a line like that, we wanted to return to the first example? The first example showed a dot plot, but every point in that dot plot goes from 1 to 10. What if we wanted to do a scatter plot, which is a lot weirder looking? In this case, the example I came up with is, what if we have, I'm going to use some terms from statistics. What if we have a population which looks like, how do I describe this? We have a population which looks kind of like the function y equals x. With statistics, you have a population which represents this variable, this equation, this function, but you won't always have, just because of random sampling from this population, there's no way that you can guarantee you'll display exactly this. Oh, in a lot of cases you can, but let's just, in most real world cases you can't. You're going to have a little bit of variance with it. So population has a variance that is not exactly y equals x, but is very close. So we want to display a function that has this sort of variance already baked into it. So the function I came up with is, I'm going to create a function here, sample float. It's going to be a utility for us. We're going to use it for a few other examples in the future. But here is a function that generates a random float value, a random decimal value between two bounds. And it generates n possible numbers. So if I pass in 10, it will give me 10 random float numbers. We're going to see this in action in just a second. But all you have to know right here is that we're going to be creating a function that gives us a random decimal value. The way that I thought about this would be a good way to do, let me erase this, and we can see what this looks like. R has a function called sample. And what sample is going to do is you pass in a range, which is a vector representing the possible values. Then you tell it the number of values to obtain and whether or not to sample from that range with replacement. So if I were to say, for instance, sample, do I have a text tool? I'm sure we have a text tool in this program. I'm going to try to type in T. Check that out. Okay. Oops. Let me increase the font size to that. Okay. So if we have, for instance, sample 1 through 10, we want to sample 10 things with replacement. This would, for instance, give us the range here would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the n here tells us we want to sample 10 things from this distribution with replacement. So our resulting set may be 3. We sample that and we put it back in the set. 3, I'm just going to give 10 random numbers. 5, 2. This has replacement, so we can possibly get the same value twice. So 3, 5, 2, 3, 9, 9, 10, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 7. Okay, there's a distribution. So this is a possible input to this value, but this function does not support floating point numbers. It only just samples from a vector, basically. So if we wanted to support random floating point values, we can say this. Let's pretend that we wanted to get random values between 0 and 1. If we can only get decimal values, let's increase this range from 0 to 10 and divide the resulting numbers by 10. Now this looks similar to us saying 0, 0, 0.1, 0.2, all the way up to 1.0. So it's a creative way of us getting decimal values from a sampling program, a sampling function, which does not implicitly support decimal values. We get the domain, we increase it, and then we divide the result. So I guess a very easier way you can do this is by saying, I don't know why I didn't think of this in the first place. If we were to get the min and the max, and we were to just use the sep function, maybe this will just work. Maybe I should just use this instead. We'll do both ways just to display it. No, actually, let's just do this new way. I think this will just work out the same. We would do minimum, maximum, and we have a step of like 0.1. So instead of doing this weird sort of convoluted increase the minimum and the maximum and we divide it by the step size, okay, let's just use this instead. They're both the same. I just realized this first one is actually a lot better while I'm writing this code. So let's represent that. So we're going to say our range is equal to is it sep? Let me go back to there. I think it is sep. Seq, not sep. I was trying to think of what's the acronym for sep? That's separator. That's for the paste function. Okay, for the sequence. With the minimum value is going to be min in this function we just created here. Min, max is the maximum value. The step is going to be, let's just do 0.001. Maybe that's a lot. No, it's fine. We'll see. Okay, then we want to return something corresponding. We want to basically sample from this range, from this vector of values. We want to retrieve values from there, and we want to replace values as we get them. So return sample is going to sample from that distribution, from the range of values. We want to sample n values. In this case, n comes from the parameter. And we want to say replacement is equal to true. I think this is just fine. We'll see. If I said sample float between 2 and 5, I'm going to sample 10 things from there. Look at that. And they're all 3 decimals long, just because I said the step size right here is 3 decimals. If I wanted to have a larger step, if I wanted to have more precision, then I can just increase or decrease 0.001 to something smaller, 0.0001, for instance. But that probably has adverse effects to memory, I'm sure. Or maybe it doesn't. Who knows? I'm not sure how vectors are represented in memory. Okay, anyways. So now that we have this sampling function, let's do this sort of toy program we just said. The population looks like y equals x, so it looks like a straight line, but it has a variance. So let's make our sampling distribution here. On the example on the left, you can see this if you would like to look at this instead. I created a function that was inlined, This is called an anonymous function. Earlier, I basically did an example where I was creating a function, storing that into a variable, and then using that variable to pass into the fmap function. You can do that inline, where you define the function inside of where it will be used. Well, let's just look at, if you look at this over here, basically I'm skipping the step where I assign it to a variable. And you could do that if you like. Let's just do the long way. So f distribution is going to equal to a function with a variable x. This needs to return x plus some kind of variance. Return x plus, let's sample a single float between, just make up something here, random, between -5 and +5 with just a single value. So it's going to be pretty close to y equals x, but it's going to have that random variance. And if we wanted to plot a scatter plot, all we do is we just say x and y there. So just like in that first example, we don't need all those fancy, in this case with a scatter plot, we do not want to make this the type of the graph to be L or O, because those will do a line graph, and that would not make sense in the context of this program. So here, I did not define what x actually is. I'm going to say x is going to be, previously we said x is all the values between 1 and 10, for instance, or 1 and 100. That would not make sense for this type of program. For this type of program, we're sampling from a distribution, so there's no guarantee that all these values are going to be ordered. If you do a survey and you ask 100 people what their ages are, you can say that the x-axis is their, I don't know, education or something, and the y-axis is their age. So you should probably notice that as their education becomes higher, their age will also become higher because of the time it takes to get those credentials. So similarly, let's, instead of setting a range like this, where it's all nice and neat, evenly distributed, let's say that the x-axis is also a sample of between 0 and 100, let's say, and there's n values of it. I'll just say n is arbitrarily 100. So there's 100 data points between 0 and 100. If we print out x, it's going to be this. So I want to have y values that correspond to this. So I want to map the x values to this f distribution function. So let's just do that as we've been doing it before. Fmap, our function we made earlier, we're mapping x to f distribution. And if we print out y, it looks like this. Pretty simple. You can notice that each point here is pretty similar to the x value, except it has this little variance added to it. So it makes it either higher or lower. Now if I wanted to plot it, all I do is I just plot x and y. And we can just end it right there. We don't have to add any other labels or colors or text or anything, or a legend or anything. So here, I'm just going to plot x and y. And check it out, nice little trend line we've just made. If we wanted to combine what we just talked about in the previous part, where we also display the line of best fit, for instance, I made up that the line of best fit was y equals x. So in other words, that's similar to plotting a line with 2 points on it. A point at 0, 0, and a point at 100, 100. So if we keep that open and we say lines, the x of the lines is equal to c, 0, 0. C, 0, 100. There's 2 data points at 0 and at 100. And then the y of the lines is c, 0, 100. The type of the line is L. And what's the last thing? Did I have anything else in my example? Lines. You can change the line width and stuff, but we don't really need to do that. That's fine. And there we go. This is like our line of best fit. You can change the line to a dotted line or whatever. It's all fine. But there we go. So this is a very common graph you'll probably want to display. You have some kind of distribution. You won't have something as simple as this where you put in just the 2 points that make up the line of best fit. You'll probably need to calculate that, usually with linear regression of some kind. But the point is that this is how you can display that once you do calculate it. So let's move on to another weirder example. Okay, so the example we just showed is what happens when we have an underlying distribution that has variance. And we want to display that with a line graph and a scatter plot. So let's do just a simple pie chart right now. This one, we can just look at the left side for this one. I'll display the very simple version first, on the right side. So if I want to display a pie chart, all I have to do here first is just display, I have a list of values. Let's say values. I'll make it different from the left side. V is a list of values. So it's a vector. And I'll set this vector equal to 100, 90, 70, 120, 180. So if this represents a pie chart, then the slice of the pie that is the largest is going to be the last item here. It has a lot more area. It's going to be twice as big as the second thing in this vector, which is 90. So those are my values. I want to associate these with labels. So I'll say labels is equal to, just to make it from the left side, lab is equal to, let's make up something arbitrary here. Milk, eggs, cheese, water, 1, 2, 3, 4, cereal. So final part, if I want to display a pie chart with these values, I can just say pie v lab. And look at that, pretty good. So that's a very simple pie chart. There's a lot more customization we can do. Let me actually run this code to see some of that customization, just so we don't have to be doing a lot of typing and fiddling. The first thing we can do is that, what if we wanted to run that pie chart with different colors inside of it? Let's look at this. Before I do that, a way that previously I was saying the R command to run this in like a REPL, this interpretive environment. If I wanted to just run the entire script, in this case the script is stored in 3, or is it? Yeah, 3graphics.r. If I want to run that entire thing, I can run the R script command. Again, RStudio has a very similar thing. So R script is going to run this entire source file. In this situation, this specific situation, you may notice that this does not display those plots to the screen. This actually plots those into a PDF. If I were to view that rplots.pdf, then it's those same graphs we made earlier. Here's my pie chart that shows this example, this long example right here. The pie chart has different colors. You can either set those colors to strings like we did before, or you can set them to RGB values. These RGB values can be only between 0 and 1. They can't be higher or lower. So not 255, as you may be familiar with. Then, let's say you wanted to do something very common, which is you have the label that you defined in the labels section that we just did with the eggs, milk, cheese, all that stuff. But you also want to display the value of the pie chart next to it. A very simple way you can do this is by creating a new string with paste, the paste command we've seen before. And we're going to be adding together the label and the value itself along with parentheses to make it look nice. So that's a very easy way that we can display both the label and the value of that section as well. And if we combine this with our legend that we saw previously, but I think the difference between this and the previous legend is that the previous legend, before I say anything, the previous legend had this call section. If we change that to fill instead of call, then it fills in solid boxes instead of those lines, as we saw earlier, like here. Here it did lines, we can fill them into solid boxes. Last thing that we can do here is in the pie chart, we can say init.angle. If you know like a unit circle, from if you've ever taken like a trigonometry class, the unit circle has the starting angle be directly to the right for the first item. If we do 90, it makes the first item rotate 90 degrees to the left, and now that's why A starts directly upwards. It's all up to preference. So that is an example of a pie chart. And again, all this has the same sort of tools we saw before with the plot. We can add a main label. There's different kinds of customizations we can do. I encourage you to look up the documentation for this when you're doing this for real. But there's a pie chart. And there's only 2 more things left in this video, then we're all done. I've been talking for a long time. The next thing is going to be a bar plot. A bar plot is very easy to do for us. Let me go back to my REPL here. I shouldn't have done that actually. I just remembered if I exit here, then I exit the things I typed in previously. Let's keep with this example that I just did. Okay, I already ran the code, so I don't need to run it again. Here is an example of a bar chart. So a bar chart is a list of discrete values, and each of those values have a certain magnitude that's positive. I think you can also do negative. Maybe it goes downwards, but it shouldn't normally be. No, I shouldn't say that. So you can do negative as well. But it's supposed to represent some kind of magnitude. So we pass in the labels. In this case, there is no concept in a bar chart of an x-axis, which is unlike a scatter plot, for example, where each point has an x value. For a bar chart, you can pass in each label instead as the x values. So here I define my y values, for instance, 1845, 1845. And then I can define the labels of each of those with names.arg. That defines the labels of each of those bar plots. And there's other sort of miscellaneous customization things I can do. I can change the color of each bar plot. Instead of using these strings, I could do the RGB like I showed before. I can display the density. The density here corresponds to how many lines are drawn inside of the plots. A higher number means a higher density of those fill lines. And I can also change the angle of those fill lines. Usually what you'll do is that if you're making a paper or something with this program, you'll want to change the angle and the density of the bar plot in case the person who's reading your paper printed it out in black and white. So you don't want to rely solely on color, for example, because if they printed it in black and white, they won't be able to see that color. So that's an example of customization for a bar plot. The final thing we can do, which is an example I really like, and an example we're going to be talking about just a little bit more, is a histogram. So a histogram is meant to represent a continuous distribution. So if we were to have here a graph, let's say that we have a sampling distribution, okay? The sampling distribution is meant to represent, for example, ages of people in college. Or let's say specifically for this college class. Let me make that a little more clear, because that just to demonstrate our example. Ages of people in this class. I'm completely guessing on this, but what I'm assuming is that most people are probably like 23 years old. I think in the United States, a bachelor's degree for most people goes from 18 to 22. So a 4-year degree. So I'm assuming this is a master's course, so most of us are probably 1 year older than that. So 23 is going to be the mean. There's some people who are older than that, and there's some people who are younger than that, and there's even less people who are younger than that, and even less people who are younger than or older than that. So 23 is the most. 22 to 24, that's like medium. And then 21 to 25, that is low. So if I were to select a random person in this class, this is about the probability that I will select one that is, for instance, 24. It's not going to be that high. There's going to be multiple people in the class who are 24, but the chance of me selecting someone who is 23 completely randomly is higher than that. So if you're hearing this, if you're thinking of a distribution that represents this, the distribution that should immediately spring to mind is the normal distribution, which looks like a curve, a bell curve, like this. We say that the middle point is called the mean of the bell curve. The mean in this case is 23. The standard deviation tells us this sort of section. How far apart are these values here? In this case, from the top rung of this ladder to the second section, there's a difference of 1. Then there's a difference of 1 between the next rung of the ladder. So that is called the standard deviation. And it defines this sort of range here. So 23, 24, 25, 26. The height of this represents the probability of selecting someone. So in this case, the probability of selecting someone who is 23 years old is very high. The probability of selecting someone who is 26, very, very, very low. Okay. Now that we have this, this is called the normal distribution, okay? We can plug in an x value here, for instance, an age, like 26, and we can retrieve what's the probability we will get someone who is 26 years old on if we completely randomly sample this class. So in other words, this distribution we'll call n. We plug in an age, and this gives us a probability. We can do this in our code, and that is done with the dnorm function. The dnorm function allows us to construct a normal distribution and to plug in an x value and obtain a probability from that. If we want the inverse of this, so we want to plug in a probability and obtain an age, then we do the qnorm function. Qnorm is just the inverse of the dnorm. So I want to plug in a probability and get an age. So it's the inverse of a normal distribution. Or it's still a normal distribution. It's just we're reversing these variables here. I'll stop drawing now. There's a lot of drawing that I've just done. So here, I'm making a function to represent this distribution the same way we've done before. This distribution is different from our previous ones in which there is no concept of an x-axis. For this is similar to me asking everyone in the class, what's your age? And then there is no input I'm telling them before that. I'm not telling them that I'm not getting other values from them. All I'm getting from them is their age. So there's no input to that function. I'm just asking people, what's your age? What's your age? So this function is not going to have an input. The idea is just I'm just asking random people. I want to randomly get a single person from this class. Let me actually remove this V part. It probably makes things a little more confusing. I did actually remove it in the actual functions. Let me just take this out entirely because it doesn't make all that much sense. Okay. So here, we have our probability of selecting a random person. It's between 0 and 1. So in other words, I want to plug in 0 represents, I guess, a 0-year-old, right? And then 1 represents, a 1,000,000-year-old or something like that. Probably the normal distribution doesn't do that, but that's the idea. If I were to do 0.001, this is probably going to give us like a 16-year-old. 0.999 is probably going to give us like a 30-year-old, for example. So that's just how integrals work. That's the probability aspect of it. But the idea is that I plug in a random probability and it should give us an age. So here, we can represent that with the QNorm function. I plug in a probability between 0 and 1, a single value, and the mean of our class, earlier I said it was 23, now we're saying it's 22. And earlier I said the standard deviation was 1, now we're just saying it's 0.8, just to make things more interesting. And now this distribution, the idea is that when I call this function, it should give us a single random age. The random age can be 0, it can be 10, it can be 100 or whatever. But the random ages should be clustered around 22. It should be, most of the random ages should be 22. Because that's just for our class that we're predicting. All right, and now just to make things more interesting here, we're gonna be obtaining 1,000 samples. This class only has, I think, less than 20 people in it, or around that number, so it wouldn't be accurate for us. But if we assume our class had 1,000 people, then we can do this. So we define a list of 1,000 people, we make a vector to store these ages, and we continually sample from this distribution. We're saying, give me the age of one person, then we resample from the distribution, give me the age of the next person, all the way down. This method is similar to you, for instance, going in your class and asking 1,000 random people in the class, what are their ages? So you can replace this part with a CSV file is what I mean. And now finally, what is a histogram? A histogram, if we think about it, is a bar chart, but the bars are all right next to each other. Because I changed this, let me close it and reopen it, and then we just run this. And now, here's what our sampling histogram looks like. What a histogram does is it gets all of the x values, and there's no concept of a y-axis here. You notice how all I'm doing for this in our graphics function here, I'm just plugging in the x values. X in this case represents a bunch of ages, like 22, 22, 23, 22, 21, 22, 22. And so we want to see how often do we get someone whose age is 22? How often do we get someone whose age is 26? And this is what a histogram is used for. A histogram is used for visualizing a continuous distribution. That's the main idea. So by passing in the hist function with an input value of x, which is the distribution ages, it will group those into different buckets, and then it will display them in this nice little format here. And of course, we can change the x label, the y label, the name of the graph, things like that. Instead of doing the frequency being a count of values, you can change that to be a percentage. So the top one would probably be like 50%, then down here would be like 30%, things like that. Just like remember, this is supposed to represent a normal distribution, which is why it looks like this, because we use the QNorm function. And I think that's everything. So that's a very broad introduction to this programming language. Man, we talked for a long time. So just to reiterate, if you want, you can go through that W3 Schools website. I don't know if I can... W3 Schools, does this work? Yeah, it is called W3 Schools. You can type in R, and then R tutorial right here. Pretty good tutorial. This is just what I described here in this video. So if you prefer that, then go there. I'm assuming you've already watched this entire video, so I don't know why you could go there for reference, but if you've made it this far, I'm sure you're an expert in this language, so congratulations. But next time we're going to be talking about RStudio and how we can utilize that to do cool things, but this is the big idea about R. So we can use it to parse a lot of data, to make graphs for it. A lot of times we can use this to make graphs for papers. A lot of papers use RStudio for making their graphs, which is cool. I've done it before. But anyways, thanks for watching. If you have any questions, contact me. Unless this is in the future, I'm only a TA for the 2024 class, so don't email me if you don't know me. But all right, thanks for watching.